Hi, welcome to Sam's Maths Lectures. This is my second lecture on set theory. So this lecture I'm going to start introducing axiomatic set theory, which is sort of a set of fundamental rules for how sets work. So initially one might think that a set is just a collection of objects, okay? And for most purposes this is adequate and it gets us by without ever really thinking too much about what a collection of objects really is or does, okay? But let's sort of go down that route and take the collection. Let's define some capital X to be the collection, not set, collection of all elements little x which do not contain themselves. Okay, so every element which doesn't contain itself, or every set which doesn't contain itself, belongs to this collection big X. Okay. Well, let's say that X belongs to itself. Well, that means that X no longer qualifies to belong to itself, which implies that X does belong to itself, and that implies that it doesn't, and it breaks. So this is called Russell's paradox, and it's sort of the motivating reason, or one of the main motivations for creating more axiomatic structure of set theory. So what we're going to do is we're going to start by saying that there's this thing U called the universe, and this is the collection, not set, collection of all sets. Okay, so every set, we start by saying that there's this thing called a universe, and every set is part of this universe, okay, which seems suitable or reasonable, okay. And then what we do after that is we're going to define a relation, membership. So a relation, recall, is a predicate of two variables and x, and then this sort of epsilon, or in x, in y. Okay, that's a relation, and it's defined on the whole universe. Okay, and then what we're going to do is we are going to sort of define two new ones off of that. Okay, first actually, so x is a member of y is sort of what this means. Although we can sort of ignore the idea of sets containing each other and just say that sets are a thing and this is a relation on sets. We don't necessarily need the burden of meaning, okay? And then this gives us two new relations which are fairly similar. So if we put a slash through it, then we just define this as the negation of x and y. So x is not a member of y. And if we write it backwards, then that is just y is in x. Okay. Sometimes it's more convenient to write things backwards. Okay. Now let's talk about our quantifiers. So I said previously that the sort of for all and existence quantifiers would have a contextual sort of thing that they run over. And in this case, that thing that they run over is the universe of all sets. So when we say for all x, we mean for every set x. Okay, and so we can define a new relation by x is a subset of y, and that is defined as equivalent to the statement for all a. So for every member a of the universe, if a is in x, then a is in y. Okay, so every member of x is a member of y, so x is some subset of y. And likewise we have x is not a subset of y, and we have x is a superset of y. And then subset. And then we also have a proper subset. So x is a proper subset of y, which we define as meaning that x is a subset of y, and there exists some member A of the universe such that A is a member of Y and A is not a member of X. So Y is X plus something. Okay. And likewise we have is not a proper subset of and is a superset of. Okay. So those are our sort of new relations. And then we also have new quantifiers that sort of make things shorter. So for here we've got for all A and X implies A and Y. A sort of nicer way to say that would be for every member A of X, A is a member of Y. And so we define for all X in, let's say for all A in X, P of A, with some predicate P, then this is defined as being equivalent to the statement for all A in the universe. If A is in X, then P of A is true. Okay, so whenever A is part of this subset X, then P of A is true. So obviously for every member of the subset X, A is true. Okay, and likewise, there exists an A in X, P of A means that there exists an A. There exists an A such that A is in X and P of A is true, or the negation of for all A and X, not P of A. Okay, so these help us run over sets sort of more briefly and makes things faster to write. Okay, and we can also sort of write for all A comma B and X to mean for all A and X, for all B and X, and so on. Just to sort of make things shorter. Okay, so now we can start talking about our axioms of set theory. So I'm going to be using some form of these Melo-Frankel axioms. There are 8 of them, plus the axiom of choice, which I'll get into later. And so we're going to start with the axiom of extensionality. Which says that sets are equal if and only if they have the same members. Okay. Same members. Okay, so in symbols, we could say for all X, for every set X in the universe, for every set Y in the universe, if for every set A in the universe, A is a member of X, if and only if A is a member of Y, then this is equivalent to X and Y being the same set. Okay, so that makes sense intuitively, because if X contains every element that Y contains and Y contains every element that X contains, then obviously they're the same set. And so this means that sort of, or you could say that X is equal to Y is equivalent to X is a subset of Y and Y is a subset of X. Okay, that's another way we can say this. Yeah, and the converse of this first statement holds, because obviously we can, if they're equal, we can just change which letter we use to refer to this set. So obviously whenever A is in X, we can just rewrite that as A is in Y. Okay. So importantly, this means that only the actual members themselves count, and so things like ordering of the members and repeats of the members don't matter. So if we write sort of A, B as a set, this is then equal to the set B, A, and that is also equal to the set sort of A, B, because, you know, the A's cancel out. Okay. So we also, now that we can talk about equality of sets, we can define 2 new quantifiers. So there exists a unique X such that P of X. So there exists some X which satisfies P of X, but only one X satisfies this. Okay, so what we could say is that first of all, there exists an x such that p of x, but also for all x and for all x prime, if p of x is true and p of x prime is true, so they both satisfy p, then we must have that they are the same set, this sort of unique set that satisfies it. Okay, and then we can have there exists a unique a in x such that p of a is a sort of simple extension of there exists a unique a such that p of a is true, but also a is a member of x. Okay, so that's the axiom of extensionality sorted. Next we have the axiom of the empty set, or axiom on the empty set. Okay, the empty set, which says that there exists a set with no elements. Okay, so this is our sort of basic, it's our sort of smallest set, it doesn't contain anything. Okay, and so in symbols there exists some element x in the universe such that for every element a in the universe, a is not contained in x. Okay. Sometimes this is written as sort of the collection of all a such that a does not equal to a, but we are sort of trying to avoid collections at the moment, so we won't use that. We'll sort of cross it out. Okay, so we have that. Then for every set B in the universe, then we have for every element A in the universe, if A is in X, sort of the same X as before, implies that A is in B. Okay, and this is using X falso quodlibet because this is always false, because obviously A is never in X by definition, and so this whole statement is always true. And so therefore for every element B of the universe, the empty subset X is a subset of B. Okay, which is important because it means that suppose X, Y are empty, then X is a subset of Y, but also Y is a subset of X using the above reasoning, and therefore X is equal to Y, so the empty set is unique. There's only one set with 0 elements. It is unique, and we call that sort of the empty set, and it's a 0 with a slash. Okay. Now then, okay. So we've started off by saying this is how two sets are equal, and there's a set with nothing in it, which is all very useful, but it doesn't really tell us how to create sets. So our next few axioms are going to do that. So we're going to start with the axiom on pair sets. Okay, given any two sets, there exists a set whose elements are precisely those sets. So whose elements are precisely those sets. Okay, so what does that mean? So in symbols, for all x and for all y, there exists a set A such that for every element z if Z is in A, then we must have that either Z is X or not and, Z is Y. Okay, so for every element of A is either X or Y, and X and Y are both elements of A. Okay, so, and we can sort of immediately see that any two sets defined in this way are the same by having the same elements, and so we write this as the set X, Y. Okay. This is sort of useful. It's our first building block. It allows us to create sets of two elements, and it also allows us to create sets of one element because we can simply pair X with itself, XX, which is equal to X. Okay, so we can create sets with one element and we can create sets with two elements. That's not particularly useful yet, but it's sort of about to be enhanced by our fourth axiom, which is the axiom on unions. Okay, so given any set X, there exists a set, or there is a set, whose elements are precisely the elements of X. The elements of X. Okay, so what does this mean? For every set X, there exists a set, we'll call it U for now, such that for every element A, if A is in U, then that is true if and only if there exists some set X such that A is a member of S and S is a member of X. Okay. So what does this mean? Whenever A is part of this union set, then there's some member of X which contains A, and so we're grouping these together. Okay. And because it's specified as having precisely the elements of X, that means it must be unique. There is only a single union set, and so we write it as sort of cup X like that, or the union of X. And this isn't sort of the most common notation for the union, but it'll do for now. And then inductively we can now create any finite set, because if we have elements A, B, C, blah blah blah, then we can create the set A, B, and so on. So then we can create the set which contains these two. And keep the rest the same, which we can then union, and the union of this is going to be just the pair set A, B. But then we can create this set and pair it with C, which will give us, when we union of this, we'll get A, B, C, and so on. So we can create any finite set in this process. It doesn't work for infinite sets because we sort of have to keep this process going to infinity, and so we're going to say that we just can't. Okay, that's probably enough for this lecture, so I will be back next time with 2 more building axioms, I think. Yep, 2 more building axioms and sort of how they work to finish the process of building sets. Okay, thanks for listening.